Witam Państwa bardzo serdecznie w imieniu Fundacji Platforma Przemysłu Przyszłości. Nazywam się Maciej Markowski i mam przyjemność powitać Państwa na pierwszym wydarzeniu inaugurującym nasz cykl webinariów. Dzisiejsze spotkanie z profesorem Dieterem Wegenerem prowadzone będzie w języku angielskim, więc pozwolę sobie kontynuować już dalej w tym języku. Ladies and gentlemen, it is my pleasure to welcome Professor Dieter Wegener, the Head of External Cooperation in the Siemens Corporate Technology, who is also the speaker of zwei Management Team Industry 4.0, the German Electrical and Electronic Manufacturers Association. Moreover, Professor Wegener is also the Executive Board Member of the Digital Europe Association, and the topic of today's webinar is Industry 4.0, the big picture. I would also like to invite you to ask questions using the chat box at the bottom of the screen. And now I would like to invite Professor Wegener to take the floor. Dieter, can you hear me?
Hear you very well. Good afternoon, ladies and gentlemen. This is Dieter Wegener speaking from Germany, and I'm really happy to be in the virtual room to share with you Industry 4.0, the big picture. And I just have to clarify, can you see my presentation?
I think that yes, now we have it.
So the presentation is Industry 4.0, the big picture. I'm presenting with two roles. One is the Siemens role. I'm Vice President and Head of the External Cooperation at Siemens Corporate Technology. And when I show Siemens slides, then I have the Siemens hat on my head. And when you show the slides like this, the ZVE2, then I'm in the speaker role of the ZVE Management Team Industry 4.0. So now I go through the presentation. It is approximately 90 slides, but I try to be fast, but not too fast. And please, in your questions and answers, the best thing would be that you say the slide number that I can refer to this to give you an answer regarding this slide. But first I want to present. So the presentation it's 5 chapters. I start with the economic viewpoint, digitalization of economy. Digitalization of economy is leading to a connected world. That means you have 5 application fields, Industry 4.0 for factories and mother factories and daughter factories and logistic partners. You have the world of smart homes and smart buildings. You have the world of the smart grid. You have the world of all kinds of mobility, cars, bicycles, trucks, trains, airplanes, ships. And then you have the world of people, in this case, when they are connected via healthcare devices. And this we call connected world, when each device is connected with each other and the human beings. When you analyze this world, which will we have in the future, you will come to this slide. You see again the 5 application fields, Industry 4.0, smart energy, smart mobility, smart health, smart home. And here it's very important. You have here the Internet of Things, where you connect all the things, all the machines with the Internet. And also you have the Internet of Services, where you connect, where you take the data coming from the devices and analyze them and put them as a service in the Internet of Services. And now it's very important. Here, in the world of the machines, in the world you can touch, you have the so-called analogous economy, which means you have a machine tool which makes out of a raw material a product. And then you distribute the product with a logistics partner from the factory to the customer location. And that is the so-called analogous economy, which you know very well, because we are working since decades in this analogous economy. And the first part of digitalization of economy means that you digitalize this process chain of the analogous economy to make it more effective, more productive, more faster, and to get higher qualities. Second is, and that is very important to understand, when you take the data coming from the machines and you analyze them with software tools, then you form up a digital product, which is like the product is a physical world, but consisting of data, analyzed data. And this analyzed data you can also share with your customers, but your logistic partner is not anymore a truck, but it's the internet which transports this smart data as a smart service to any node on the world in the internet, and the customer can take this from the node and can take it, whether he has to pay for this or he gets it for free. It depends on what you define with him. And so you will get a digital economy here based on the smart services, which is based on the analysis of data coming from the Internet of Things. That is very important to understand. And that is the new business which you can create based on digital analysis of the data coming from this world. Okay, that is very important to understand. And to make it simple, here you get revenue by selling machines, and you get, I call them analogous euros, and here you get digital euros by selling smart services, to make it simple. That is now the very simple description of what is digitalization of economy. It has two effects, first and second effect. So with that, I go now in the application field of Industry 4.0 to explain it in detail. And now I want to describe how the data comes from here to here and will come to smart services. Now I go to slide 5. So slide 5 is explaining digital economy. And that you see here, you see the machines and all those things and devices. They are called OT devices, operational technology devices. And then you take the data, and then you have a world of IoT platform, Internet of Things platform, which takes this data. It will store this data in cloud, and then you will put software as apps working on this IoT platform, which is nothing else as an operating system for apps for the platform, and then it takes the data and then makes smart services. So here you see the digital value add you create in this platform is that you take the big data from the bottom, from the machines, and you will analyze that with the apps at the level of software as a service layer. And then you will generate smart data, and this smart data you distribute via internet as a smart service to the customers. The opposite between the analogous world and the digital world is here the logistic partner is the internet, and the internet is working with the speed of light and for free. And you know, in the physical world, you have to pay for the logistic partner, like to pay for the truck, for the gasoline, and for all those service he provides to you. That is the big difference, the timing and the price. And I will give you then later examples for digital value add. Now I go to the Industry 4.0, and I like to explain to you how it works. Now, to explain this, first you have to understand the principle of three dimensions in Industry 4.0. First dimension is the digitalization of the value chain. You come from a factory to a smart factory. Second is that you digitalize the product. You come from a product to a smart product. And then the third is that you create smart services, as I have explained before, based on the big data you analyze from the machines in the shop floor. And that's all. These are the three dimensions of Industry 4.0. And now I want to explain you in an example how it works in detail. For this, I want first to share with you what is a smart product. On the right-hand side, you see a machine tool from a German manufacturer, 3M. This is a machine tool, and the person in blue color is the blue collar worker, and he's operating the machine. And this is a real machine. And normally when he prepares a job on this machine, he has to stop the machine, and then he has to prepare the next job. He has to program the details of what he has to work on the machine. And then the machine is not running. It's waiting until he is ready with programming. And that takes a lot of time. And of course, in this period, when he prepares the next job, the machine is unproductive from a business viewpoint because it's not producing parts and products on the machine. And so on the left-hand side, you see also a machine, and that is to explain the digital twin of this machine. Inside the machine, there is a controller. In this case, it's a controller from Siemens. It's called C-numeric, which is the CNC controller for this. And then we make a software, which is an emulation of the C-numeric here on a PC, on a laptop. This is on the left-hand side. And this has the same functionality on the laptop as on the real machine. And then the benefit is that this blue collar worker can run the machine, and parallelly from the time view, he can prepare the next job on the machine with the same interface on the machine as he has normally on the real machine. And this he can use to save time. And of course, the machine is still running and is still productive. And during this, he saves approximately 80% of the setup and configuration time of the real machine. And this is cost saving. And that means overall, in this case, he can increase the productivity of the machine by 10%. And that is much. And he can do it. And the good thing is he can do the laptop. He can take the laptop also in his home office and can prepare the next job, or he can prepare it from a different room or location. So you can do it from a remote location. That is perfect. So that is digital twin, virtual machine, and in the end, it's a simulation of the real machine with a simulation tool, which is here given in the laptop. Okay. Now, with that, I want to explain you now what is a factory. And first, I have to explain how to come from a factory to a smart factory. You remember the digitalization of the value chain means that you take an existing factory, brownfield, and then you digitalize the value chain of this brownfield factory. And I did it with an example to make it clearer to you. So I take a real, that is a test assembly line for test and training sessions. And so I take this, and the principle is given here on the right-hand side. And can you see now slide 12? Now that is the principle of the factory. So you have a feeding station where you put small bottles on the conveyor belt. Then you have a conveyor belt which goes around like a circle. And then you have a station 1 where you put on the glass bottle a small white or red, white and red heads. And then it goes back on the conveyor belt and goes to the sorting station in a specific manner. And second, you have a station 2 where you put blue and red heads on it. And so you can program the whole thing with a controller. And to measure and to steer that, you have also a lot of sensors within this station. And this is a classical assembly line, which is automated. Now, on page 14, you see now how it looks like. You see on the left-hand side the cupboard with the controller, and here you see in the heart the Simatic S7-1500 is a modern controller of Siemens, and other boxes which you need to steer all those equipment, okay? And this is called automation technology, the whole thing. There's a controller and the the inverters and the power supplies, which drives all those sensors and actuators here. You see here an actuator, a drive, here's a drive, here's a drive, and so on. So, and you see valves for the sorting stations, and you see traffic lights and all those things. That is all covered by one controller. So now look, to digitalize this analogous setup, this analogous assembly line, you have to do three parts. First, you make it in part one, you use a CAD software for the design of the whole assembly line. Second, and you see here, you see here, that is NX11, it's a brand name of our CAD software at Siemens. And then you have, second, you need a simulation software to simulate all the functionality of this, what you have designed. That means you look at the physical movements of the bottles on the conveyor belt during operation. You can simulate it with the so-called NX11 MCD, and MCD stands for Mechatronic Concept Designer, which is nothing else as a simulation of the physical laws with respect to this setup. And then you can look whether how, for example, is the speed of the conveyor belt, and you can increase it until the bottles fall down due to the centrifugal forces of here in the curve, for example. It is simulated by this. And third, that is part two, and the third is the simulation of the automation itself. So you have the schematic, you have the simulation of the schematic in the computer, where you can see whether how it works in the simulation, the automated system, what you have done, of what you have programmed. Okay? And with these three parts, you make out of a factory a smart factory. And how it looks like. You see here the feeding station. And you see here what the bottles come. And here you see the sorting station, how it goes out. So with this factory, conventional factory, I want now to show you how to make from a conventional factory, which you perhaps have at your home, at your company, how to put a smart service in to improve this existing factory. So you take a brownfield assessment, a brownfield situation in your factory, and now you make a smart service to improve the situation. Now I explain the smart service. So it's the same factory as you have. In it there are the sensors, as you know. Then you have the setup, and you have this automation cupboard. And now you put in a Mind Connect Nano box. And this Mind Connect Nano box, why do you need it? I show you. This is this box. Here is the assembly line. You take all the data coming from the sensors over time, the time series, and you put in the Mind Connect Nano box, and then you connect this Mind Connect Nano box to a IoT platform from Siemens. It's called MindSphere, which is the operating system for the IoT platform. And here you program now software, you take software from this platform and you apply now this time series with the processor software, with the learner software. You simulate the controller, you simulate the user interface, that stands for service-oriented architecture user interface. You have databases to store the data coming from the time series. And then you have an operating planning system where you say how the assembly line should sort these bottles. And with that, you improve the situation. And now on page 24, you must see the video with the optimized behavior. So on the MindSphere platform, you have machine learning software, which optimize the setup of this by looking for the best solution to solve this task which you put in the operation planning. So you say in which sequence you want to have the bottles, and then you say you should do it in a fast manner, as fast as possible. And so the machine learning software will do it in the platform, in the Mindful platform, using simulation software to optimize the whole process. And then you will see in the next slide on a video, I hope you will see left and right system, unoptimized and optimized system. It is a little bit difficult because of the streaming effect. But in real, you will see that the left-hand side, which is unoptimized, will take longer than the right-hand side, which is optimized. Now I show you better here the result. With that approach, with the smart service approach, and using artificial intelligence, we have optimized this assembly line by 31.4% faster than before, without saying the machine what it's doing. So the artificial intelligence software didn't know what is about the assembly line. It just got this task to optimize this sorting problem. Okay, so it is really helpful to apply artificial intelligence software to existing factories, and you see here the effect that you can get high increases in improvement of the efficiency. Okay. Now, what do you have to invest? You take the existing brownfield setup, the assembly line. And what you have to do, you have to buy the MindConnect Nano box. I think it costs 800 euro. And then you need to apply software from Siemens or from other companies, if you like. But at least in this case, a cloud integration software, simulation license for this simulation stuff, and the app development, you need some software for this. And in this setup, we had a break even within 1 year to make it here. And it was very easy for the people to do it because they don't have to program, they just have to apply software. And you can train it very, very fast with the people to use it. Okay? So that was the example, what you can do with smart services in existing factories to improve them, using new software tools, including machine learning software. So, now I want to come to the next chapter, German Initiative Industry 4.0. The main idea is to set up the digital economy, as I have already explained before, to make digital value, to make the digital economy feasible to the existing factories. For this, we developed the concept of the asset administration shell. You take a machine, and with the machine and an asset administration shell, you create a so-called Industry 4.0 component. So the definition of an Industry 4.0 component is you take any IoT device plus an asset administration shell, and that is it. That is an Industry 4.0 component. So to do this, we have to define, to apply this concept of this Industry 4.0 component, we created, or we founded the so-called Industry 4.0 management team at Z4E. These are all the members of this community. These are approximately 145 members from approximately 90 companies and institutes. Okay? And when you see its organization, then the management team at Z4E, it was founded in October 2013. So more than 6 years ago. And I was elected to become the speaker of this. And I was nominated in January 2014. So at least I'm in the 7th year in the speaker role. So, and what we did is we create an organization here with so-called mirror committees for different purposes, strategy and use cases, models and specifications, research, security, and other things. And this is looking from the Z4E viewpoint, that means from the automation industry, from the electrical and electronic manufacturers view. And then we create documents and views which we share with the platform Industry 4.0, which was hosted by the Ministry of Economy and the Ministry of Research in Germany. And they have a similar setup. So we can put these experts in this group and so on, so that they are working very well together. Okay. Now, so the main task is you take the analogous value add, product development, production, and service, very simplified. And the biggest challenge today is that they don't work together, those process steps. So there is the interoperability between those different steps is not high. So one of the big steps is here, the challenge is to create an interoperability in the shop floor where the machines are standing, so that every machine can talk to each other machine, and to connect these machines with the office floor where you have the servers and laptops, which could be connected to the internet. And to show that, to make that happen, we created this Industry 4.0 component to have a setup how to structure that. And now on the page 44, you will see, and this is something you know already, in the shop floor where the machines are, it is a big difference, a big variations, whether you are working in the energy field or in the water or the chemicals field or oil and gas industry, pulp and paper, or in the marine industry or automotive or aerospace or electronics. So each branch has a different setup. And what we try to create is the Industry 4.0 component is defined that it is able to be connected under all those branches. So an Industry 4.0 component in chemicals will understand also an Industry 4.0 component in food and beverage. So from a technical viewpoint, so they can talk to each other on a technical view. And for this, it's very important to use already norms and standards which are existing, because the machines are already designed and will be in future time also designed regarding these norms and standards. And second, that we talk about a reference architecture model which should be used to handle that. And for this purpose, we create also the Rami 4.0, which I think you know already, which is the so-called reference architecture model Industry 4.0, which is nothing else as here is the Industry 4.0 component. That is any machine, and then you have an asset administration shell, which creates an Industry 4.0 compatible communication. So each Industry 4.0 component can talk to each other, to any other Industry 4.0 component using this communication principle. That is by definition. And to structure that administration shell, we use the reference architecture model, which is a three-dimensional model on the right-hand side. So what we did is we take an existing definition of the life cycle in this dimension, in the horizontal dimension, regarding the IEC 62890 standard. And on the architecture level, we use the hierarchy levels regarding the IEC 62264 or IEC 61512. That means we take existing international standards which describe the hierarchy levels to come from product to the work center to an enterprise until the connected world. And you remember in one of the first slides I shared with you the definition of the connected world with the 5 application fields: Industry 4.0, smart grid, smart home, smart mobility, and health as a smart health. Okay, so now when I go one level deeper of the Rami model, then I take out the communication layer, this layer, the blue one. When I take this communication layer and look what is it, then I see this on the page 36. Now you see the so-called OSI7, OSI7 layer model, 7 layers. And what you can see here, what we did already in the Industry 4.0 management team, here's the Rami model, the life cycle, the architecture level, and here you see the communication defined by the OSI7 model. And here you see, for example, in the production phase, we have defined you can take a wire or a wireless approach. And when you have a wire, then you have, of course, for the data link an Ethernet. And for the transport network mechanism, you take TCP/IP. So you have normally TCP/IP, Ethernet, and a cable, a LAN wire. When you are wireless, for example, wireless LAN, Wi-Fi, then you are wireless, you have Wi-Fi, and then you take for the transport network mechanism a TCP/IP mechanism. So that is the communication model. And then in the future, we will have for the wire, the TSN, the time-sensitive network technology developed, and for wireless, the 5G, as you know. And for this, it's important that we prepare also Industry 4.0. And exactly this chart, you see why in Germany we have, let me say, made a lot of effort to the government that we get for 5G an exclusive bandwidth of 100 megahertz bandwidth for Industry 4.0 applications in the factory. So now in Germany, we are allowed to use 5G frequencies in the factory exclusively in the frequency band from 3.7 gigahertz till 3.8 gigahertz. And that is something we should also cover in Europe, and we are working on Z4E and other associations to work on this, that we cover this out, that we roll this out in Europe, but we are still on the way. But in Germany, it's already decided by the government that we can use 5G at the factory exclusively for Industry 4.0. And then it's important, when you go up in the level, OSI7 level 5, 6, 7, there you describe the assets. For example, if you have a temperature probe that you say, what is the curve? Do you use centigrade, grad Celsius, or do you use Fahrenheit or something else? That you define here. And for this, we propose the OPC UA standard, which is safe. So this is already covered in the Industry 4.0 approach. So for those who are involved in these details, it's very important that you see in the future, we will communicate via TSN plus OPC UA when you take a wire, and when you are wireless, you have 5G plus OPC UA standard for communication for Industry 4.0. That means, I show again slide 35. This is the definition of the communication layers here for this communication. Now we can go on the next slide. And so in the end, you will have all the machines, and with the administration shell, they could be working on one IT server landscape, whether it's private or public, you can define, but then you can achieve that every component will talk to any other, and that they can work along this value chain in a factory, along the life cycle, okay? So now I'm ready with that, and just to remain, the purpose of this is that you connect all the devices with that world of the digital economy, and the enabler is the Industry 4.0 component with the asset administration shell. On page 38, you have already seen. So standardization is very crucial for the whole thing. So in the analogous economy, you have for the different levels Here is the electric technology. Here's all other technologies. Here's telecommunication technology. You have different organizations which are covering these things. In Germany, you have for the standardization the DIN and the DKA. In Europe, you have Senelec for electrical stuff, Sen for mechanics, and ETSI for telecommunication. And in the world, you know, IEC, ISO, ITU for telecommunication. But to be honest, IT is not covered here. And what is IT about? And that is very important to understand. In the IT, it is you have a different approach. You see again this chart with the 5 application fields with the Internet of Things and with the Internet of Services. And here you have a so-called standardization zoo, because these are a lot of logos of consortial standards organizations which are be used in the internet. And for example, here you see the Wi-Fi standard. Here E-class, W3C, Thread, and perhaps others, LoRa and others. So what I want to say is, for IT standardization, you don't go with this normal standardization organization, but you go with those consortial standardization. And it is very important to understand, it is not only these are covering the Internet of Services here above, but you go also in these application fields. And now you see, for example, here in Industry 4.0, here is OPC Foundation, which I covered in the previous slide. I showed you that we take OPC UA standard for the OZ7 level 567. That was meant by this. So you see, now it's easier to understand what we are doing here in this Industry 4.0 management. Okay? And now the question is what to use. Should we use the standards, normal, the fully consent-based standards, or the standardization zoo? And for this purpose, we create this triangle. We create the platform Industry 4.0 I already shared. And now we create two new organizations, the Labs Network Industry 4.0, that we have that is a community in which we can share the use cases in the test rigs we have. And here, the Standardization Council Industry 4.0, as the name says, is a council where you steer the standardization efforts. And you can see on the next slide, 43, that is it's founded by this group: Bitkom, Z4E, VDMA, DKA, DIN, and Industry 4.0 platform. And what we do is we take what we want to achieve in the Industry 4.0 platform, in the strategy, we look in the Labs network which is working, which use case is working, and which use case is necessitating which standard. And then we decide here in the Standardization Council whether we go this way or the standardization way, okay? And we create a roadmap and a standard, a map for the standardization for Industry 4.0. And each year we create a so-called DIN DKA standardization roadmap Industry 4.0. Each year issued normally on the Hannover Fair in April. For those who are more interested, there are some details, but I skip them. Now I show 46. And now now you can relax. Now I share with you the view of Siemens on this, just in some slides and some small animations, so you can relax and just listen, because now I'm leaving the theoretical and conceptual view. So Siemens, you know, we have a new organization starting April 2019. We have three big divisions: gas and power, smart infrastructure, and digital industries. And we have three strategic companies: mobility, Siemens Gamesa, and Siemens Healthineers. And we have, of course, corporate partners, and I'm working in the corporate technology at the bottom, which is belonging to the corporate development box. So, and what you see in the newspapers, there is announced that gas and power and Siemens Gamesa will merge and will go to the stock market in September this year. We will see whether Corona is changing this a little bit, but in the end, it's decided that this will be a merger. And then we have this here, Siemens Energy. So next is what is our business model? In the end, we have the devices. You remember the Z4E chart. Then we have electrical components and automation components. Then we have an IoT operating system, the MindSphere. And then we share Siemens software. To be honest, you have to pay for this. And we share Siemens digital services you can create on your own, but you have also to pay for using this software. And then we have a consulting company which helps you in integrating these at your factory. And besides this, we are working on these technology fields on the left-hand side: data analysis, artificial intelligence, simulation tools, cloud and platforms, secure networking, cybersecurity. We have a huge amount of experts worldwide who are keen on working on these technologies. So, and now I come to Industry 4.0. I think you know this chart, the history of Industry 1.0, 2.0, 3.0, 4.0. Industry 4.0 has one task: to use data from design, engineering, production, and performance to improve the productivity and the flexibility of your factory and of your setup in your real world. And for this, we have the product. It's called Digital Enterprise. And what is Digital Enterprise? It is something which gives you, I share slide 50, shows you the three dimensions of Industry 4.0, and this is the Z4E concept chart. And now I share slide. Now it's a marketing slide of Siemens. You see here the Siemens logo. Our three dimensions are digital twin product, digital twin production, digital twin performance. It is just the wording of Siemens marketing, but it's the same concept, the same approach as I mentioned on the Z4E slides. And now I want to give you here an example. Very important is you make first the design of a product virtually, then you make the production also virtually, all in the computer, and then you go in the real production where you have a real setup, a real factory, and then you have a real product. So very important to understand, left-hand side is virtual, right-hand side is real. And for this, you must understand you have the real world right, the left, the virtual world left. And for this, you need a huge amount of software portfolio. And you see here just MindSphere at the bottom, at the top for the IoT platform operating system, and below the Team Center, Commerce, Plant Side software schemes as for the process flows. And all those boxes are representing software tools and software suites to handle all those things you see here. Simit I mentioned, here NX CAD software, here's NX CAD. And so all this is covered under this, and these are thousands of different software tools you can use if you work with Siemens together. And just to give you an idea, Siemens invested 10 billion euros, more than 10 billion euros over the last 10 years in acquiring companies to be able to offer this to our customer base. Just to give you an idea on that. Now you come to 53 and you see here the whole thing in this left leading software portfolio for the simulation world. left-hand side and leading automation portfolio for the right-hand side for the real, and in between all those things which I already explained to simulate it. And now I want to give you an example out of the automotive industry. So I go on slide 55. Now I share with you some video animations. Unfortunately, because of the streaming effect, it could be that it is a little bit slowly, but I try my best on this. So you see, first you have to design the car, for example, the car body, and then you have to see the video animation of this mechanics. Yeah, I just shared. You can simulate everything: mechanics, stiffness, airflows, and also a wind tunnel, which is shared here. Then you have to think about the electrical system, for example, the cabling. And for this, you have to define the cable systems in the car. And so look at the video. You can design it as you work with Work and Excel. You just drop and down, drag and drop, and then you can design that. And you can put in electronics, you can simulate the heat flow, you can also simulate the ventilator to cool down the PCBs. So everything can you simulate with our software. Next is you have to incorporate embedded software, for example, to create a display. Here is shown a display in the car. This is not anymore mechanical. That is just a display, an LCD display, which you have to program. And most of the software is open source software, which you put in as embedded software in your design of the car display. And that I show how to work. You define the structure of the display, you define the architecture, you say what software you want to connect, then you put in the open source software, you implement it, and you also integrate the documentation of this, and some parts of this will be done automatically. And in the end, you have software, embedded software, which you can put on your hardware in the car, in the hardware boxes. Now, that was the design of the product, which you did virtually for mechanics, for electric, and for software. So now we have to go into the production, and first in the production process. So we are in the car, you see the car body, you see the robot. Wow, now it's working. The thing is, we take from KUKA the description of the robot and just implement it in our simulation tools. So you can simulate a KUKA robot or an ABB robot or a FANUC robot if you like, and you put the assembly line on. And then you go on the production line because you need not only one robot. Can you see now? So you say, okay, I need 3 robots, and you can make the simulation of the 3 robots. And you see on the left-hand side, just drag and drop from the menu, you can put in. And if you want to have a 4th robot, then you take a 4th one, copy and paste. The same as you work with Word or Excel. And then you work, and then you simulate it. Now, when you have the production line set up, you can also simulate this production line to see whether it works and whether the production level you want to achieve is achieved by this setup. And if it's not, then you can modify until you are happy. And then you go in the total factory, in the entire factory, and then look what happened. Now you see the entire factory working. You see the robots, everything in a 3D set up. You can look in the factory before you put it up in the erection. You just see it in the front. You can share it with your customers, those things, everything. Now, when you have done this, then the most important point comes when you go from the virtual world into the real world. And as you know, I don't know how many people are attending this webinar, and I'm not sure how many people have experience in commissioning of a factory, but at least you know it's crucial, it's difficult, and it takes a lot of time. So what we can offer is a simulation of the commissioning. We call it virtual commissioning, where we simulate. Can you see the robots from ABB? They are working in a virtual world, and you simulate the working of the robots, And that is exactly the software you need to program the robots in working in this situation. And then we look in the semantic, because for the virtual commissioning, you need the emulated semantic, the emulation of the controller. Because we are the designer of the semantic, of course, we are able to make an emulation of the controller. That is not so difficult. So what you have in the virtual commissioning setup is for a high amount of percentage, for example, more than 95%, is exactly what you need on the source code to program the semantic in the real world. So look, now you are in the real factory where the real robots of ABB are now working in the real factory. And the good thing is that the erecting time goes down by a significant amount of time. You will become faster and faster in the setup. You will save weeks, to say in detail. Now, after virtual commissioning, you are now going in the real factory, in the real production, and now see what happens. Now you see the real factory. Of course, in this case, we share a lot of Siemens products, which we sold to the customer, and also to the software tools we share like this with the customer. Everything comes under the roof of digital enterprise. Now, after the reproduction, you want to optimize, and for this Internet of Things, you take all the data coming from the devices, and then you try to optimize the performance. And now look in. For this, you need MindSphere to connect all those devices. And now I want to share with you a case in the a use case where we are in our own factory. So that is an assembly line in the electrical EWA, that is EWA, that is our semantic. So there's a factory where the semantic are produced, and this is an assembly line where it's the welding stations and so on. And so to make these PCBs on this welding line, it's very important to have a high quality rate. We have 12 DPMs, that means 12 defects per million. That means a quality level of 99.9988%. And to achieve this, we have not only have good components in the machine line, but also we have to test, to measure with an X-ray machine each PCB board. But then the volume of the factory comes up, and the X-ray was in a bottleneck. And for this, the people say we need a new X-ray machine for 500,000 euros for each line. And the factory boss said, no, that's too much money. Think about another approach. And so they made the following. They took more than 40,000 production parameters over time for each line and go into an edge device from Siemens, put it on the MindSphere, apply an artificial intelligence scheme, train the artificial intelligence software on this data, and the software learned after some thousands rounds virtually how to improve, and then it comes up with an algorithm with a solution where to say, here we don't need to measure on the X-ray, we can just say it's at the quality level you want to achieve, and by this we save 500,000 euros for the new machine with the same level of quality, the 99.9988%, and we have set up 30% we saved in necessary X-ray tests for this purpose, just by using existing standard of the shelf software, artificial intelligence software. Okay, that was the first case. So I took more time than expected. So the question is whether I share two other use cases, or we can just skip and are open for questions, answers. I'm open-minded. We will share the whole file as a PDF. Shall we stop and we make questions and answers?
We are slightly running out of time, so we wouldn't like to use too much of time of you and our participants. But there is a couple of questions coming in, also including my email. And one of the questions that I got was, can you give us some hints how to start increasing the awareness on importance of Rami 4.0 modeling compliance in Poland? You can see it in the chat window as well.
Yeah, I think we are just starting with that. So the first point is that at least the community should understand the main idea, the main concept, the main principles we are working on in Germany. And we invite you all in Poland to work with us on that, because it's in the end, it's standardization stuff. We have to create standards which are regarding to this Rami model capable. So the easiest thing is that you go into your standardization organization and helps us together to bring up these standards in an international level. They are so, but for this you need to go more in the details, because it is not one standard, there is a couple of standards who are related to this. But the easy things could be that we perhaps make a session when Corona is over, when I can be allowed to travel. Then I can come to Poland, and then we make a bigger session, for example, a big workshop where I can start with a keynote session and explain it again, but then we go in sessions and go in more details if you like. I can offer this. But I think because of Corona, it will take at least half a year until I'm able to travel, or more than 6 months.
Unfortunately, and I think that we would all be looking forward for this. See on the chat that everybody are strongly looking forward to it. So strong invitation for you to come and visit us here and work with us and share your experience here much more. So I think that right now what we would do is that I think that I can express our warmest gratitude to you and great thank you for your presentation. Of course, we will share it in the PDF as you requested. And now I will switch a little bit for just a short moment into Polish to say thank you to everyone. Szanowni, bardzo dziękujemy za udział w naszym webinarze. Mam nadzieję, że podobał się Państwu wykład pana profesora i na pewno będzie, jak Państwo słyszeliście, będziemy mieli okazję jeszcze z panem profesorem się spotkać. Korzystając z okazji, chciałbym zaprosić na nasze kolejne wydarzenie, kolejny webinar z naszego cyklu już za tydzień, 6 maja. Szczegóły będą dostępne na naszej stronie niebawem oraz przez różne kanały komunikacji, również social media. Będzie poświęcony tematu WK, a Przemysł 4.0 i będziemy gościć pana doktora Witolda Jankowskiego z Instytutu ICANN. Jak również chciałbym zwrócić Państwu uwagę, że w przygotowaniu jest seria Przemysł w czasach COVID, która będzie poświęcona różnym ciekawym case'om, jak polskie firmy dostosowały się do rzeczywistości w naszych trudnych czasach w aspektach produktowych, ludzkich, a także transformacji modelu biznesowego. Więcej szczegółów i więcej informacji wkrótce na stronie przemysłprzyszłości.gov.pl. Ja bardzo serdecznie Państwu dziękuję za uwagę i mam nadzieję, że będziemy mieli okazję się z Państwem spotkać. Dieter, any last words for you?
First of all, I really appreciate that we met on the 9th of March in Warsaw, where we have created the idea to make a session to continue on our collaboration. And I must say I'm really impressed to have 109 attendees, participants in this webinar, which are interested in Industry 4.0. And I already said to you, I'm willing to offer 4 another meetings with you and your community, and please feel free to set them up. And I'm really interested in setting up in Poland, together with the Z4E Association, a collaboration scheme. That means that we try to help Poland to come into this Industry 4.0 community, and we have to find out what is the best way, but at least we are motivated, and I think it's a fantastic idea to make it over your platform Industry 4.0 in Poland, because we have already this platform, so we can use this organization. And I'd like to thank you all attendants and participants today that you are interested in this. And of course, sorry that I can't finish the 2 use cases, but I think when you look in, then you perhaps see the slides, you can understand what is meant. There's an example of Hella, a machine tool producer on using artificial intelligence to improve the machine tool storage, and there's a third example of additive manufacturing together with a Hewlett Packard company, which we did with Siemens. Thank you
Great.
to all of you, and thank you for participating.
Thank you very much, and we appreciate you very much. Thank you, and hopefully see you very soon. Have a good day, everyone.
You're welcome.